In this video, we're going to go ahead and cover this particular integral, something that involves partial fraction decomposition and specifically the cover-up method. I'm sure you heard of partial fraction decomposition many times. You've seen it in a pre-calculus class, and I'm sure now you're going to see it in a calculus class. And we're going to cover the cover-up method, which is something that's heavily used in order to solve something like this. But why exactly do we cover partial fraction decomposition? Well, it's kind of like in the heart of Laplace transforms. So if you wanted to study engineering or solve any sort of differential equations, the Laplace transform uses partial fraction decomposition to solve those things. So let's go ahead and discuss this particular method. So what we have is the integral of 2x plus 2 all over x squared plus 8x plus 15. So we have a rational function that we're integrating. And one of the things that you'll notice right away is that the bottom can be factored out, and that's actually a blessing for us. So let's see, what two numbers multiply to 15 and add to 8? Well, that looks like that's going to be 3 and 5. So we're going to rewrite our integral as integral of 2x plus 2 all over x plus 3 times x plus 5 with respect to dx. So all we've done so far is just rewrite the integral so that we can better understand it. Now, here's the idea of partial fraction decomposition. This means that we can take this integral and we can rewrite it as a sum of two rational functions where the denominators are the particular factors that we just found. Now, what is a and b? We don't know, but we're going to figure that out in a second. So how do we go about it? The idea is that if you were to take these values and if you were to get common denominators, you will have to multiply the top and bottom by x plus 5 here on the first fraction. And on the second one, you will have to multiply the top and bottom by x plus 3. If you notice, we have the same common denominator, which is basically the denominator that we have here. So this integral is 2x plus 2 all over x plus 3 times x plus 5 with respect to x, and this integral up here will become integral of a, x plus 5, plus b, x plus 3, all over x plus 3 times x plus 5 with respect to x. Now, look at that. We have the same denominator on the bottom, and on the top we have this sum of a and some factor plus b and this other factor. So since the bottoms here are equal to each other, well, that means the numerators have to be equal to each other. And that's exactly what we're going to focus on. So we find the value of a and b. Let's go ahead and do this on the other side, on the right side of the blackboard. Well, 2x plus 2 has to equal to this. So 2x plus 2 has to equal to a times x plus 5 plus b times x plus 3. And again, this is a blessing for us. Whenever you have linear factors as our factors, this is good because we can go ahead and use the cover-up method, which is exactly what we're supposed to do in this particular video. Well, how does it go? Well, we want to find the values of a and b. So what we're going to go ahead and do is find something that's going to cover this up. And what I mean by that is find a value of x that will make this equal to 0. So this can go away. What is that value? Well, negative 5 plus 5 is 0, so that's exactly what we're going to go with. So we're going to have x is equal to negative 5. That's a choice that we're going to choose, or a value that we're going to choose, and we're going to go ahead and plug it in for every value of x. So we have 2 times negative 5 plus 2 equals, and then on this side, like I mentioned, this is negative 5 plus 5, which is 0, so this entire thing goes away. So we really just have b times negative 5 plus 3. So let's go ahead and simplify this. Oh, on the left side here, we have negative 10 plus 2 equals, and then we have negative 2b. Let's go ahead and simplify further. This gives me negative 8 is equal to negative 2b. In other words, if we divide the negative 2 to the other side, we're going to get that 4 is equal to b. So this is perfect because we found the value of b. All right, let's go ahead and find the other value. Let's go ahead and go to the next parentheses and cover this up. What will we have to choose in order for this to go away? Well, that's negative 3. So x is equal to negative 3. And now in this case, I'm going to do some simplifying pretty quickly. I'm not going to write everything down. But just imagine, I'm going to do 2 times negative 3, which is negative 6, plus 2. That's going to be negative 4 equals negative 3 plus 5 is going to be negative 2. This is going to give us negative 2b right there. Okay, and then now we're going to have, it's going to be negative 2a. And in this case, this portion is going to go away. Now you're about to notice that I actually made an algebraic mistake, and this is what happens when you don't show your work. I'm very guilty of this. When I plugged in -3 up here and I add 5, I should get a +2, not a -2. So that should have been a 2a right there. Again, sometimes mathematicians make mistakes, and that's okay, as long as you catch it ahead of time. Beautiful. Let's go ahead and divide this to the other side, giving us -2 is equal to a. And this is amazing because we found the two values that we needed in order to rewrite our integral. So now that we have a and b, this particular integral right here is 2x plus 2 over x plus 3 times x plus 5 dx is now equal to the integral up here where a is -2. So we have integral of -2 over x plus 3 plus, and then b is 4. So we have 4 over x plus 5 with respect to x. And now all we have to do is integrate this right here. You're essentially using u substitution where our u value is x plus 3. But that's just going to be our du, our differential will just be dx. So I'm hoping that in this case, you can understand how I'm going to rewrite this. This will become -2 natural log of the absolute value of x plus 3 plus 4 natural log of the absolute value of x plus 5. And now don't forget your plus cheese in this particular integral. This is how we solve this particular problem when you're dealing with rational functions where the denominator can be factored out. We use partial fraction decomposition, we get the cover method, and at the end we get our solution that's all based in terms of natural logs. Pretty sweet, I would say. And I'm sure you have other questions like, what happens when our denominators can be factored out, but they're quadratics, or perhaps there's multiplicities? That's something that we can talk about in a later video. Perhaps I'll make a video right after this one. And if so, I'll make sure to link it in the description below. But in the meantime, please feel free to subscribe to this channel, follow me on Instagram and on TikTok, and I'll see you in the next one.